First, let's define the standard basis vectors of R3. They are E1 equals 1, 0, 0, E2 equals 0, 1, 0, and E3 equals 0, 0, 1. These three vectors are useful because any vector x equals x1, x2, and x3 in R3 can be written in terms of the standard basis vectors as x1 E1 plus x2 E2 plus x3 E3. This notion will be discussed in detail when we study vector spaces. Let A equals A1, A2, A3, B equals B1, B2, B3, and C equals C1, C2, C3 be vectors in R3. We define the vector product, which is also called the cross product, of A and B as follows. We write A cross B equals the determinant of E1, E2, E3, A1, A2, A3, B1, B2, B3, where E1, E2, and E3 are the standard basis vectors we've just defined. We can expand the determinant along the first row to give the determinant of A2, A3, B2, B3 times E1 minus the determinant of A1, A3, B1, B3 times E2 plus the determinant of A1, A2, B1, B2 times E3. Expanding the determinants, we have the vector A2, B3 minus A3, B2, A3, B1 minus A1, B3, A1, B2 minus A2, B1. In other words, the vector product of two vectors gives another vector, which is different from the scalar product of two vectors, which gives a scalar. The vector product is easily remembered using the 3×3 determinant. Secondly, we define the scalar triple product of A, B, and C as A dot bracket B cross C. Using the definition of the vector product, we get the vector A1, A2, A3 dot B2, C3 minus B3, C2, B3, C1 minus B1, C3, B1, C2 minus B2, C1. This equals A1 times the determinant of B2, B3, C2, C3 minus A2 times the determinant of B1, B3, C1, C3 plus A3 times the determinant of B1, B2, C1, C2. This can be written as the 3×3 determinant A1, A2, A3, B1, B2, B3, C1, C2, C3, which is equal to the previous expression by expanding along the first row. We can easily remember the scalar triple product of three vectors using this determinant. Let's look at an example. The vector product of 1, -1, 0 and 3, 0, 1 equals the determinant of E1, E2, E3, 1, -1, 0, 3, 0, 1, which equals the determinant of -1, 0, 0, 1 times E1 minus the determinant of 1, 0, 3, 1 times E2 plus the determinant of 1, -1, 3, 0 times E3, which equals the vector -1, -1, 3. Also, we can easily verify that E1 cross E2 equals E3, E2 cross E3 equals E1, E3 cross E1 equals E2. Now, let's prove some properties of vector product. Let A, B, and C be any vectors in R3, and K be a real number. The first property is that A cross B is perpendicular to both A and B. To show this, we compute A dot bracket A cross B, which equals the determinant of A1, A2, A3, A1, A2, A3, B1, B2, B3. Since the first two rows are identical, this determinant is 0, which means that A cross B is perpendicular to A. Similarly, B dot bracket A cross B equals the determinant of B1, B2, B3, A1, A2, A3, B1, B2, B3. Since the first and the third rows are identical, the determinant is 0, so A cross B is perpendicular to B. The second property is that A cross 0 equals 0 cross A equals 0. Indeed, A cross 0 equals the determinant of E1, E2, E3, A1, A2, A3, 0, 0, 0. Since the third row is a 0 row, the determinant is 0. Similarly, 0 cross A equals the determinant of E1, E2, E3, 0, 0, 0, A1, A2, A3. Since the second row is a 0 row, this determinant is also 0. The third property is that A cross A equals 0. Indeed, A cross A equals the determinant of E1, E2, E3, A1, A2, A3, A1, A2, A3. Since the last two rows are identical, the determinant is 0. The sixth property, A cross bracket B plus C equals bracket A cross B plus bracket A cross C. By definition, A cross bracket B plus C equals the determinant of E1, E2, E3, A1, A2, A3, B1 plus C1, B2 plus C2, B3 plus C3. This equals bracket A2 times B3 plus C3 minus A3 times bracket B2 plus C2 times E1 minus bracket A1 times B3 plus C3 minus A3 times bracket B1 plus C1 times E2 plus bracket A1 times bracket B2 plus C2 minus A2 times bracket B1 plus C1 times E3. This equals the vector A2b3 minus A3b2, A3b1 minus A1b3, A1b2 minus A2b1, plus A2c3 minus A3c2, A3c1 minus A1c3, A1c2 minus A2c1, which equals bracket A cross B plus bracket A cross C. The seventh property, bracket A plus B cross C equals bracket A cross C plus bracket B cross C. We can check that both sides are equal using the components of the vectors. Here we will use the previous properties instead. Bracket A plus B cross C equals negative bracket C cross bracket A plus B using the fourth property, which equals negative of bracket C cross A plus bracket C cross B using the sixth property. This equals the negative of C cross A minus C cross B, which equals A cross C plus B cross C using the fourth property.